Okay friends, how are you? So I think you are doing well. So today I came up with a new lesson as an extension to the previous lesson on Mooney viscosity and stress relaxation. Today I want to discuss with you how to measure the vulcanization characteristics of rubber compounds which contains sulfur and accelerators using Mooney viscometer. So I think you know the things related to Mooney viscometer, and we'll see today how to measure the vulcanization characteristics of rubber compounds using Mooney viscometer. Right. So before that, we need to know what is vulcanization. Right, so what this is. So here this is the polymer chain or the repeating unit of the 1,4-cis polyisoprene, that is the polymer of natural rubber. I took it as an example here, right? So you know this is the crepe rubber. So even in ribbed smoked sheet rubber, whatever the type of natural rubber, it contains this long chain molecule, the polymer 1,4-cis polyisoprene. So what are the characteristics of this polymer? So it has a large molecular weight and high molecular weight distribution, since the N number is very high. So here you can see a allylic hydrogen atom, and here methyl group, here the unsaturated carbon double bond. So due to the presence of this type of bonds, these are vulcanizable using sulfur like materials, right? So here, what are the ingredients that we mix with our rubber to make it vulcanizable product, right? So examples are sulfur, right? The sulfur is a yellowish color powder which can be used to make vulcanizations between, which can be used to make cross links between polymer chains. And MDT is one example for accelerator. So sulfur itself and the heat can vulcanize this type of polymer, right? But the speed is very less. So to increase the reaction rate, we use accelerators. And normally we use zinc oxide and stearic acid together in rubber compounds as activators, and as an activator system, right? Zinc oxide and stearic acid. Right. So once we mix these materials, sulfur, MBT, accelerators and activators, with rubber, what will happen to that is called rubber compound, right? So it is more processable, means flowing. It can flow under pressure and temperature, right? So then we can use it to make it to make different shapes, right? If the product shape is different, right, we can mold this compound because it is processable, so easily flowing under temperature and pressure, right? So then the elasticity is less, right? Since once we make this compound, the elasticity of this rubber compound is less. On the other hand, the strength of this material is less. We will learn these things later, but at the moment you have to keep these things in your mind, right? So rubber itself between compounding ingredients has less strength, right? No use without increasing these strength properties and elastic properties. But the processability is important in processing steps, because we need to shape our rubber product maybe into a tire, a ball, or whatever the product, right? So it should be more processable under this stage, compound stage. But at the product, let's take an example, a tire, right? The tire compound is more processable, that's why we can shape that compound into a tire, right? But think of a tire, right? It is more elastic and it has big strength, right? So but the compound has less strength and less elasticity and high processability. So we'll see how we convert these properties into high elastic and high strength, right? So that is the cross-linking where the vulcanization occurs, right? Here you can see rubber molecules, C1,4,6 polyisoprene, that is this, right? So if we take two chains like this, right, then we add sulfur and temperature, heat, right? If we need to speed up this process, we can use accelerators also here. Let's say accelerators are there, right? So then it makes cross links like this, right? Actually it makes sulfur bonds between rubber chains, that is called making cross links, right? Once the cross links are formed, see, sulfur cross links, right, the rubber material will get harder, the elastic properties will be increased and the strength properties are increased, right? So to improve these elastic hardness and strength properties, we need to vulcanize the rubber, right? So your tire, your eraser, your shoe, your slippers, whatever the material you are used, which is made of rubber, is a vulcanized rubber product. That's why you feel these properties in those products, right? But the compound used for this, it is more processable with less these properties, right? So it's like making a cake, right? So the compound or the mix we use to make a cake is more processable. We can shape it into different shapes, right? If you want to star-like cake or a ball-like cake or oval-shaped cake, so we can shape it, right? So that is processable. But the other properties, the cushioning effect or the hardness of that cake is less. But once you apply heat, right, in your oven, right, you will make your cake, right? So it is somewhat harder, it has good cushioning effect, right? And different types of properties are there, right? Once you make it usable product, right? Likewise it is same here side, here it makes sulfur cross links and improve these properties. So we are going to measure how this is happen. So what is the rate of this reaction, how fast it is making cross links, right? We are going to measure it using the Mooney viscometer, right? So how to measure it, right? So those are called Keogh characteristics or vulcanization properties, or like using those terms, right? So both are same, right? So we use Mooney viscometer. I use this MVR to denote Mooney viscometer. So test procedure is this, and the temperature is defined for different compounds in this test procedure, but it normally depends on the working temperature that the processing temperature or the vulcanization temperature that we are used in the in our production lines, right? Or else if we need to check which temperature is more suitable, so we can vary it and measure, right? So it depends, right? Then we need to heat our dies and the rotor before the test, right? So if you have any doubt in this regard, see our previous video, right? Then we have to weigh the required sample and that compound sample has to be fixed to the rotor. Maybe it is a large rotor or the small rotor, but normally we use large rotor, right? But it should be done as quick as possible, because once if we take more time to fix our rubber compound sample, maybe the weight, I cannot say the exact weight, but because it depends on the specific gravity, since the volume of the chamber of the testing cavity volume of the testing cavity of Mooney viscometer is a constant, right? So a specific gravity is a constant of the rubber compound. If you know these two, you can calculate the weight that should be taken from the rubber compound to make the sample, right? So we need to fix it very quickly, because the temperature can reduce from the rotor, right, since it is heated up to the temperature required, right? So then we need to fix the rotor with the sample into the testing cavity, right? Then close the cavity and run the test using Workbench or Enterprise Online Manager, both softwares, right? So this is the shape of typical vulcanization curve that we are going to obtain from the Mooney viscometer using large rotor, right? The x-axis is the time in minutes, y-axis is for Mooney units. Actually it measures the torque, but it converts that torque into an arbitrary value that is called Mooney viscosity, which is termed in Mooney units, right? Here the 1 minute time, so that time period is for preheating time, right? We allow our rubber compound to increase its temperature to the testing temperature, right? So we allow 1 minute preheating time. So what will happen after this 1 minute preheating time? Now the Mooney viscometer, the rotor rotates at 2 rpm constant rotational speed. It always try to keep that speed, right? So at the initial stage, what will fail by this rotor? Our rubber material contains rubber, sulfur, accelerators, activators, sometimes fillers, maybe whatever the things, right? The molecular weight is somewhat high, right? The material is somewhat stiff, hard, right? So that will feel by the rotor, right? So initially the rotor will feel that it needs somewhat high torque to keep its 2 rpm constant speed. So then it will give this type of peak initially, right? So once it keeps that 2 rpm rotation, right, due to the shearing action between the rotor and the compound, the molecular weight will reduce, right? The material will melt, right, under pressure. So due to that, the torque value is reducing. Due to that, the torque value is reducing now. It will come to a minimum as in Mooney viscosity. So it will come to a minimum, right? So now we are applying the temperature and a given pressure, right? Our compound contains sulfur. We are applying temperature, so it will give the heat to the compound. Once the heat and sulfur is there, what will happen? It starts to make sulfur crosslinks. Once the crosslinks are formed, what will happen to the viscosity? It will increase, right, due to temperature and the presence of sulfur and accelerators in the compound, right? The material starts to develop crosslinks among polymer molecules. Then the viscosity will increase. Again, the rotor will feel now the material is getting hardened and hardened, and the rotor will feel it requires somewhat high torque and high torque and high torque to keep its 2 rpm rotational speed, right? That's why this curve goes in this way, right? Okay, now we will receive this curve due to that principle, right? But here we need to measure some important parameters. Those are called scorch time and cure time. Scorch time and cure time. We'll see how do we measure this scorch time. So we know, if we know the minimum Mooney viscosity we obtain under the cure curve, right? So it is here. Then we need to count 5 Mooney units upward from the minimum, this here, right? From the minimum. Then we come to this point and we need to go to the curve here, and we can mark this point and we can read that point using this value, right? We can read that point. Okay, when we come down from this point to the x-axis, we will take that value called T5. This T5 is called the scorch time, where the vulcanization is started due to temperature and the presence of sulfur and accelerators in the rubber compound, right? This is called onset of vulcanization or the initiation of crosslinks. Actually it happens here, but that is not significant to measure, right? That's why we take principally and basically from the 5 Mooney units upward from the minimum Mooney viscosity, right? So we count 5 units from here, then come to the curve and go down. Then you will take this T5 time. T5 means the scorch time, right? The time taken to increase the Mooney units or the Mooney viscosity or the torque by 5 Mooney units from the minimum Mooney viscosity received, right? So that is the scorch time, where the vulcanization starts, right? So what's next? The cure time, vulcanization time, complete vulcanization, right? So that's this. We know this is T5, right? We know the minimum. Now we have to count 35 Mooney units from the minimum here to upward, right? Then we need to come to the curve, and we can read that value from here, right? Then we need to come down. Then you will find T35. That is called the cure time or the completion of vulcanization due to the presence of sulfur in the compound and the temperature given, right? Okay, here we need to count 35 Mooney units from the minimum Mooney viscosity value, right? We need to come to the curve, and if you go to the x-axis, you will find the T35, means the time taken to increase the Mooney viscosity or the torque value by 35 units from the minimum torque value or the Mooney viscosity received in the cure curve of Mooney viscometer measured using large rotor, right? So this time is T35, the vulcanization time, complete vulcanization. We call it as cure time, and T5 is this is the scorch time, right? So these two time values are very important in determining the vulcanization properties of rubber compounds using Mooney viscometer, right? Okay, here T35. So how do we measure the cure rate then, right? If you use small rotor, so I will go to the large rotor first, right here. So the cure rate index, how fast the vulcanization, how fast the curing occurs, how fast the crosslinks are formed, right, is measured using this equation T35 minus T5. We know these values from the x-axis of the curve, so we have to take this difference. If you use a small rotor, we need to measure T3 as the scorch time and T18 as the cure time, right? Means 3 Mooney units upward from the minimum torque value, and take that time is T3 scorch time if we use a small rotor. T18 means we have to count 18 Mooney units from the minimum, and we need to come to the curve and we have to take the T18, right, the time taken to increase the viscosity or the torque value by 18 Mooney units from the minimum, right, that is T18. So that is the vulcanization time or the complete crosslink formation time if you use the small rotor. That difference gives the cure rate, but here for this example this is the cure rate index, right, how fast the vulcanization occurs. Once you report this value, you have to mention what is your sample and what is the identity of your sample and the test temperature, because the temperature determines the rate of curing, right, and you have to mention the rotor, large or small, right, since you can see here the values are different, no, so we need to mention it. And minimum viscosity, you have to mention it, right, minimum viscosity, and you have to mention these values separately, right, other than the index. Here the index, the make and model of the instrument, you have to mention it, and it is very important, right. So here one example, if you have used large rotor to measure the Mooney viscosity, to measure the vulcanization properties using Mooney viscometer and using large rotor, so we have to use this equation to calculate the cure rate index, right. If time difference is less, what will happen? Time difference is less, we will find high cure rate, right, we will have high cure rate. If the time difference is large time difference means we will get low cure rate index, like this, no. If the time difference is less, see T5, T35, the time difference is less, the rate is high, the angle is high, right. If the time difference is large, see T5, maybe T35 here, right, difference is very large, right, so then we will receive less cure rate index, right. This is one example. You have to plot the typical vulcanization curve for these compounds, compound A and compound B. So what are the ingredients? Natural rubber, zinc oxide, stearic acid, sulfur, CBS, MBT. I want to say that CBS is a kind of accelerator, and MBT is also an accelerator, right. In the compound A it doesn't contain MBT, and the compound B it doesn't contain CBS. All the other ingredients are same, right. Now we are going to see how to plot the typical vulcanization characteristics, characteristic curves for these compounds, right. Okay, I will use this, and so hope you can see my board. So here our compounds, compound A and compound B, right? Before everything we need to plot our x and y axis, right? Here Mooney units, here time in minutes, right? We will first plot the compound A, right? Before that you need to know what is CBS. Actually CBS is a kind of delayed action accelerator, right? It means it can increase the scorch time and sometimes cure time, right? Sometimes the cure time, right? Sometimes it increases the cure time, right? But the rate of curing is somewhat fast. Then what about MBT? It's an fast accelerator. Scorch is less and cure time is less, right? These are the properties of these two accelerators. You may know these to plot the curves, right? So if I take MBT first, right, we need to mark here 1 minute time, right? 1 minute time, right? So then first it should show somewhat initial torque, then the torque has to be reduced, come to a minimum, and if it is MBT the rate is high, right? For compound A, this one rate is high. Okay, now we'll plot the curve for compound B, right? So it contains CBS, right? So it is delayed action, but initially after 1 minute preheating time it should heat up to some time, but the torque will not affect, right? And it should come to a minimum, and the scorch time is high and rate of vulcanization is like this, right? Compound B, right? So since both compounds have shown the same minimum value, same minimum, right? So you can count 5 Mooney units here, 5 units, then come to the curve. Then you will see here is the T5 for compound A and T5 for the compound B. Then you can count another 30 units, maybe here, then it is 35 here, right? Then come to the curve, right? Then you will see that T35 of the compound A and T35 of compound B. Right, so which is bigger, right? Here the T difference CRI B, this one CRI A, so CRI B is greater than CRI A, right? So this should be your answer, right? And you have to plot this curve, the axis, and you have to name them well, and you have to mark the preheating time, initial torque, right? You have to mark the 5 units, 35 units, and come to the curve and mark the T5 and T35 separately. Maybe you can use different colors. Then you have to give the reason for this variation. The reason is this reason, right? That is the answer for first question, right? Okay, I will erase this part now. And we shall move to the next question. Okay, it's again a nice one, right? So before everything, we have to plot the curve, axis, here more units, here time in minutes, right? And here 1 minute preheating time. Okay, first we need to think of what is the composition of the compounds, right? Here rubber, zinc oxide, stearic acid, sulfur, CBS, they have used CBS, right? But all things are same, but the compound A doesn't contain carbon black, a kind of reinforcing filler, right? And here they have used 60 pHr of carbon black. All the ingredients are given in pHr, parts per 100 parts of rubber, right? Here 60. So what carbon black can do? Carbon black, so what can it be done, right? Well, what is the use of carbon black? It reinforce, no? Reinforce the rubber. Reinforce the rubber means harden, no? It harden the rubber, right? It harden the rubber, right? So then what will happen to the torque values, right? Torque is increased, right? It increases the torque, right? So if we use, if we take the compound A, right, it should give some kind of initial torque and it will reduce to some extent and it will show this type of curve for compound A. Now we need to compare this with the compound B, right? What will happen to this torque value? What will happen to this torque value? Mi, initial torque. If I say initial torque, initial torque of compound A. So what will happen to that? Due to this carbon black in the compound B, it should be high value. Should be a higher value, right? Mi B, here A, right? Initial torque of B compound. Then what about the minimum? Here the minimum of compound A, let's say ml, minimum torque of compound A So what will be the minimum torque of compound B? It contains reinforcing filler 60 phr, so it should be somewhat high, maybe here, right? So it will reduce its viscosity value to a minimum value, and also it follows this type of curve, compound B, right? So its ml is also somewhat a high value now. Compound A here, ml compound A, and here ml of compound B, right? Okay, those are like that. And here also we have to count 5 Mooney units from here, and it will come to here, like, and we need to go to the curve like this. Then we need to come here and find T5 of compound A, and we need to, it's 5, count 35 units from the minimum. We need to count 35 units, and we need to come to the curve, then go to the x-axis, then you will find T35, right? So this is the CRI of compound A here, right? Then we'll do the same for the compound B, right? So here it is the minimum, right? Here the minimum, and we have to count 5 units, maybe here maybe 5 units, then come down to the curve, the x-axis, then you will find T5, right? So let's say the T35, 35 units from the minimum, it may be here, and have to go to the curve, right? Then maybe from here to here 5 units, and we take this much, right? Have to come to here T35. Okay, this is the CRI of compound B. Okay, so this is the cure curve for these two compounds, right? So the compound B should go above the compound A, since it contains carbon black 60 phr and it is more harder compared to compound A. But in practically sometimes the rate of vulcanization can be high in compound B, right? Since these carbon black like fillers can increase and can affect the cure rate in some cases, but here I didn't consider that point, but it can happen, right? If so, it will go in this way, then the CRIB can be reduced, right? But I didn't consider it here, right? If you need, I can plot that possibility also. T5 and those points will not be changed, but the other possibility I will draw in red color, right? So the curve can be go in this way, right? Be possible, right? It is possible to occur, right? It is possible to occur. I will plot it as B dash, right? So then see the here T5, right? Possible, right? and here you will see T35. right? Now what is the difference? CRI B dash, no? If so, CRI of B dash is greater than CRI of A, right? So this can happen, right, but not always, right? This can happen but not always, right? These two are the possibilities of B, right? But A is like this, right? So that is the answer for this question, right? We have to find another answer for the last question, right? I will delete this. And before that, everything we need to plot our axis. Here time in minutes, here Mooney units, right? And here 1 minute preheating time. Okay, what is our question? Right, so we need to plot the typical curves, vulcanization curves. Remember, it is vulcanization. The previously we learned in the previous video the Mooney viscosity curves, right? Here it is vulcanization of compounds. Since we measure the Mooney viscosity for rubber compounds even, but here we measure the vulcanization properties using Mooney viscometer, right? That's why the compounds contain sulfur, accelerators, activators, etc., right? So all the things are same here, no? Up to now, up to from this point to this point, Nr to carbon black, all the things are same. But in the B compound, it contains 2 pHr of processing oil. Once the oils are incorporated, the torque values are getting lowered, right? That's the principle. Oils reduces the torque. So that is the principle, right? Here oils reduces the torque values, but it cannot affect to the time values, right? We'll draw the first curve for the compound A. So it should show somewhat initial torque, then the minimum, and it will show this type of curve, compound A, right? It contains 60 pHr of carbon black, right? Now what we have, 2 pHr of processing oil in the compound B. Definitely the Mi values should be less, no? Here Mi of A, and here ml of A, right? And now our compound should show less ml, less mi, less ml, right? This type of curve for the compound B. Here MLB, and here MIB, right? Then what we have to do is we have to mark 5 points from the bottom, from the minimum torque value. Let's say it's here 5 points, right? 5 units, 5 more units, maybe it's this point. So we need to come to the curve A and go to the curve, the relevant time value. Then we have to go to the T35, maybe 35 Mooney units, right? And we have to come to the curve, maybe here, and you have to come to this T35. So this is that CRI A. Then we'll do the same thing for the B, maybe 5 Mooney units, maybe here, T5 and 35 Mooney units, here 5 Mooney units, right? You have to come to the curve, then you have to note the T35 of that compound, right? So this difference is CRI of compound B, right? Likewise, we have to plot these curves, and if there is something different in CRI values, or rates, so we can interpret them based on the compound properties, right? So however, this difference should be there. Since the B compound contains oil, it should show less stock values, but the rate is not changed. You can see the same result here. CRIs are more or less equal, right? Because the vulcanization system contains sulfur and accelerators, same accelerators in same amounts, 2:1 ratio, right? And all contains carbon black, and all the ingredients are same. Only difference is this, it reduces the torque value, right? So this is the answer for the last question. I hope you have got something from this lecture, and if you have any questions, you can comment them and I will provide the answers for your questions, right? Thank you for joining with us.